In order to solve the wave equations, let's first note that if the electric and magnetic fields are time harmonic, which in this class we will assume that they are, the time derivatives can be converted to multiplication by j omega. So the wave equations turn into these. We'll define the term omega times the square root of mu epsilon as k, the wave number, so that the wave equations are further simplified into these forms. Now, since the electric and magnetic fields obey the same differential equations and are expected to have the same solution, we're going to shift our focus to solving the electric field wave equation. Once we have the solution for the electric field, we can extend it to the magnetic field as well. So let's start here. We have a differential equation, the wave equation, which can be written like this. This is the differential equation we're trying to solve. We also know that the electric field is some unknown function of time and space, of x, y, z, and t. But we've made the assumption that E is time harmonic, which means it can be separated out like this. E is some function of space multiplied by a harmonic function of time. So if we plug this into the wave equation, it becomes this. And the time harmonic can be factored out of both sides of this equation, leaving this differential equation for the spatial function of E. From here, we're going to solve for E using the separation of variables technique, which begins by assuming that the function E of x, y, and z is separable. In other words, that it can be separated into a product of three terms, and that each of those three terms is a function of a single variable. We'll call the first of these terms capital X, which is a function of lowercase x. We'll call the second term capital Y, which is a function of lowercase y, and we'll call the third term capital Z, which is a function of lowercase z. And since E is a vector but we don't know its direction, we'll just give it this unit vector, A sub E, which is defined to point in the direction of the electric field. So if we plug this definition into our differential equation, this is what we get. It doesn't look like we've cleared things up much, does it? But we're heading somewhere, I promise. The next step in the separation of variables technique is to divide both sides of the differential equation by all three terms of the function. So we're dividing by x of x times y of y times z of z. This division leaves us with this result. Now, here we have something important. Each of the three terms on the left-hand side of this equation depends only on a single variable, and the sum of those three terms equals a constant. To solve this equation, all we need to do is set each of those three terms equal to a constant, and then set the sum of the three new constants equal to negative k squared. So let's do this. Let's let the first term equal a constant. We'll call it negative kx squared. And we'll let the second term equal a constant, and call this one negative ky squared. And we'll let the third term equal a constant, which we'll call negative kz squared. So if we plug all three of those into the differential equation, the equation becomes kx squared plus ky squared plus kz squared equals k squared. So what we've done is take a very complicated differential equation in three spatial variables and split it into three very simple differential equations, each in a single variable, and all three of the same form. And it turns out that this is a very familiar differential equation with well-defined solutions. Let's take the first one as an example, x of x, and look at it in three cases. Case 1 is when kx squared is 0. If the constant kx squared is equal to 0, then we can solve this differential equation through simple integration. Integrating once gives c1, a constant of integration, and integrating a second time gives c1x plus c2, a second constant of integration. In this case, the electric field is not propagating, sinusoidal in time, but not in space. Case 2 is when kx squared is less than 0. In this case, x of x is a real exponential, either exponentially increasing or exponentially decreasing. It may also be expressed in terms of hyperbolic sines and cosines. Again, this wave is sinusoidal in time, but not in space. It does not propagate. Case 3 is when kx squared is greater than 0. This is the case of greatest interest to us. In this case, the solution can be expressed either as complex exponentials or as sines and cosines. In either case, this represents a propagating wave, sinusoidal in both time and space. Each of the functions x of x, y of y, and z of z may fall into any of these three cases. Our total solution for the spatial function of the electric field is the product of all three solutions. So for instance, if all three functions fall into the propagating case 3, then this is our total solution for E of x, y, and z. Notice that this vector is pointing in the direction of the unit vector a sub e, but it is propagating in the direction of the vector k, which is equal to kx ax hat plus ky ay hat plus kz az hat. Notice that by the three-dimensional Pythagorean theorem, kx squared plus ky squared plus kz squared must equal k squared, the magnitude of the vector k, which satisfies the differential equation we started with. This wave also has wave number k, which is equal to omega times the square root of mu epsilon, and also equal to 2 pi over lambda, and it has phase velocity equal to 1 over the square root of mu epsilon. Now, this is not our final solution for the electric field. This is the solution for the spatial factor of the electric field. Remember, our total solution was E of x, y, and z times the temporal factor, e to the j omega t. So this is the total solution for the electric field. However, if written in phasor form, the time harmonic term will be suppressed, so the solution will look like this. And since E and H satisfy the same differential equation, the magnetic field solution will have the same form. Be careful though. They have the same form, but when you start solving for the coefficients, A1, B1, A2, B2, and so forth, they will be different for the two equations. The coefficients depend on the physics of the specific problem you're working on and are not generally the same for E and H. So let's look at this equation and talk a little bit about what it means. This is the most general solution for an electric wave that has propagation in all three Cartesian directions, x, y, and z. There are 6 terms because for each direction there's the possibility of a forward propagating wave, traveling for instance in the positive x direction, and of a backward propagating wave, traveling perhaps in the negative x direction. The direction of propagation for each term is found in the exponent. So this term, a1e to the negative jkxx, has an amplitude of a1 and is propagating in the positive x direction. That's important to remember. The exponent is negative, but propagation is in the positive x direction. This term, b1e to the plus jkxx, has an amplitude of b1 and is propagating in the negative x direction. So again, the positive exponent corresponds to propagation in the negative x direction. The total field is the product of the forward and backward waves in x times the forward and backward waves in y times the forward and backward waves in z. The field is pointing in the direction specified by a sub e.